We did free fall without air resistance last time. I want to do that again, but be a little bit more thorough in how we treat it. And then I also want to talk a little bit about free fall with air resistance. And we'll contrast and compare the two, and the numerical analysis part is just, we will try to use a computer to solve the equations that we need to. With no air resistance, I just gave you a formula. It was a quadratic function last time, and we tried to find the t-intercept, for example, for when the ball hit the ground. But what's the physics behind that? You got a ball in the air, there's a ball. It has a single force acting on it. This is the ground here. If you assume no air resistance, there's a downward force of gravity. Maybe you call that F sub grav for force due to gravity. And in the absence of air resistance, like in a vacuum, that's the only force. There's something called Newton's second law from physics that gives you what you would call an equation of motion. Probably most of you had physics in high school. Remember F equals ma? Favorite equation from high school physics. This is actually a differential equation in disguise. You have to know what the total force is. It is this force due to gravity. But what is that? Well, it's proportional. It's a constant. And it's proportional to the mass itself. The ball has mass m. And it turns out, since it's in the downward direction and the upward direction is the positive direction, positive h direction, say, you have to put a negative sign in front of it. Negative mg turns out to be the force due to gravity in the downward direction. And it's got to equal the mass times the acceleration. Yes, you can cancel the masses there. The m's cancel, but let me not quite do that yet. Let's think about standard units for things. T is time in seconds. H is height in meters. G is the acceleration due to gravity near the surface of the Earth, about 9.8 meters per second squared. Let me just put the units, meters per second, written meters per second squared as a shorthand. And the mass is m, and that in standard units would be kilograms. So thinking about the units on both sides, here the units are kilograms times, evidently, meters per second squared. And here the units are the same, kilograms times meters per second squared. These units actually simplify to just something called newtons. Capital N for newtons, or sometimes written NT for newtons, but I'll just write a capital N. The units on both sides of the equation do have to be the same. But yes, you can cancel the m's. In the absence of air resistance, the mass itself doesn't matter. And you get G is A, negative G is A. But what is A? A is the second derivative of the height with respect to time. That's an example of a differential equation. Second derivative of height with respect to time equals a constant, a negative constant, in fact. The acceleration is negative. That means when you're going upwards, you slow down. You're accelerating in the negative direction. That means you slow down. If you're already falling downward, you speed up. Once again, because the acceleration is negative. It's in the downward direction. What's the goal? The goal is to solve for h as a function of t. Well, if the second derivative is constant, you integrate it, you're going to get that constant times t plus another constant, an arbitrary integration constant. The velocity, the first derivative of h with respect to t, can be found by integrating. Go ahead and write an integral sign negative g with respect to t. to get negative gt plus c, though the c does happen to equal the initial velocity, because if you plug in t equals 0 into the right side, it simplifies to c. At time 0, the right side equals c, and at time 0, the left side equals whatever the initial velocity is. For our example, on Tuesday, it was 20. But in general, you would call the initial velocity v sub 0, or v naught for short. Naught, v naught. Don't say v naught. Say v naught, N-A-U-G-H-T. Naught as in 0. C is the initial velocity. So the velocity becomes negative gt plus v sub 0, or v naught if you prefer. But wait a minute, where's the h? Well, the velocity, the upward velocity, is the derivative of h with respect to t, so I have to integrate again if I want to find h, the height. Integrate that. H is going to be the integral of negative gt plus v naught dt. That'll be negative g over 2t squared plus v naught t plus some constant c. But that constant c, once again, has to be the same as the initial value, because when you plug in 0 into the right side, you just get c. Right? Replace t with 0, you just get c. Therefore, the final answer for the height as a function of time, call it, say, f of t, is negative g over 2 t squared plus v naught times t plus h naught. And for our example, last time, well, of course, g, we're near the surface of the Earth, that's going to be 9.8, so this becomes negative 4.9 t squared. Our initial upward velocity was positive 20 meters per second, and our initial height was 1.5. And there's the quadratic formula from last time that we set equal to 0. I should call it a quadratic function. Set it equal to 0 to solve for the time when the ball hits the ground. Use the quadratic formula. And what did we get? It was 4 something seconds. I don't remember exactly. We'll redo it with Mathematical. So that's a quick derivation of how to find the height as a function of time when there's no air resistance. Now, what about if there's some air resistance? Free fall with air resistance. It does get more complicated. And not only does it get more complicated, but the modeling is less clear. So here's our ball again. Mass still is m. There is still the gravitational force. This is F grav, which is still negative mg. But what's the air resistance? And what direction does it point? The answer is, it depends. If the ball's going upward, if you've thrown it upward and it's moving up, it's slowing down not only because of gravity, but also because of the air resistance. The air resistance would be in the downward negative direction. However, if it's falling downward, air resistance wants to push it up. The air resistance is in the upward direction. So if I draw an arrow for air resistance, well, which direction should I draw it? Either way you draw it, it's not always applicable. Let me just, for the sake of clarity in the picture, draw it upward, meaning the ball itself is falling downward. Let's say that's F air when the motion is downward. In other words, when the velocity is negative. That says air there if you can't quite read it. And I didn't write it very well. F air. What does it equal? You could hypothesize different kinds of formulas for F air. There's not a unique answer. Which one's right? The answer is it depends. It actually depends on the shape of the ball. Footballs are different than baseballs, say, are different than wiffle balls, are different than feathers. Not really a ball then. The answer for the form of FA depends. But certainly the simplest thing to try is to assume it's proportional to the velocity and in the opposite direction. Say negative k times v when k is positive, so negative k is negative. That's certainly the simplest thing to try. Doesn't mean it's the best thing to try. Maybe instead of negative k times v, we should do negative k times v squared, or v cubed, or v to the fourth power, or maybe even v to the half power. Maybe negative k times the square root of v. Or v to some weird power like 1.473. How do we know what the best power of v to use is? That's not clear. That would have to be compared against experiments, probably, to see which one might be best. But this is certainly the simplest thing to try from a modeling perspective. But again, we could be wrong. Let's see what the model would predict. We once again use Newton's second law, N2, I'll abbreviate that for short. F equals ma implies, well, I need to add the gravitational force to the air resistance force and say that equals mass times acceleration, mass times the second derivative of h with respect to t. But this is the same as negative mg minus kv. So do I integrate this to find v? No, you actually don't integrate it as is, because how would you do it? V depends on t, and you don't know what function of t it is. So how in the world would you integrate that with respect to t? M, G, and K don't depend on t, they're constants. But V depends on t. You can't simply integrate this to find V as a function of t. So what do you do? Well, you can still integrate, but you have to do something else first. Does anybody who's taken differential equations know what to do next? Besides maybe divide both sides by m as I'm doing right now. Does anybody who's taken differential equations know what to do here? You could use an integrating factor, but there's something conceivably simpler. You can do what's called separation of variables. You can effectively divide both sides by this thing and quote unquote pretend this is a fraction and quote unquote multiply both sides by dt and then integrate with respect to t. And on the right, at least, and integrate with respect to v on the left. I don't want to show you how to do that for such a complicated example here today, in case you haven't had differential equations. But it can be done. If we take, say, k equal to 1 and m equal to 1, units for m are kilograms, units for k are technically units of force per unit of velocity. Units of force being newtons, unit of velocity being meters per second. Units for k are technically newtons per meter per second, which you can simplify to newtons times seconds over meter, which hardly makes any sense, but don't worry about it. You can't really intuitively make much sense out of these units, but they are the appropriate units. And let's go ahead and use g as 9.8 meters per second squared. If we use those assumptions, the differential equation does simplify to dv dt equals negative 9.8 minus v. So it does simplify it. Oh, I'm wondering if there's something I did wrong. Is this right? I think in my PowerPoint, I might have written something different. Let me just double check here. Okay, no, that's right. Let's look at this part of the PowerPoint now. It turns out that if you separate variables and integrate, then the velocity turns out to equal this thing right there. The velocity, which is also dHdt, is negative 9.8 plus c times e to the negative t. There's an exponential decay in the velocity. Isn't that weird? We'll try to make sense out of it, but just hang with me. This is a function that solves this differential equation. Maybe we should verify that. That's worth taking the time to do. So V, this turns out to mean that V is negative, what did I have? I already forgot it. Negative 9.8 plus c e to the negative t. Is there a way to know that's right? Yeah. You can check that it solves the differential equation without actually solving the differential equation, without separating variables. How do you do that? To check that this solves the differential equation, plug it into the differential equation and see what happens. First, plug it into the left side. In other words, take its derivative with respect to t. You get 0. Then with the chain rule, minus c e to the negative t, which simplifies to minus c e to the negative t. C is an arbitrary constant. Also plug it into the right-hand side. In place of v, negative 9.8 minus v is negative 9.8 minus this thing. Simplify. The 9.8's go away. The negative sign distributes through the parentheses. And when you multiply negative 1 times this, you get negative c to the negative t. Hey, we got the exact same thing as the derivative equal. That's what it means to solve this differential equation. When you plug the function in, this is a function. We propose it solves the differential equation. I didn't show you how I derived it. I didn't do the separation of variables and integrating. You could, if you know how to do that, but I'm not assuming you do. But assuming this is right, we can always check it. We can verify that its derivative, which equals that, always equals this when you replace v with the function. This function. We got the same thing in the end. That's not going to typically happen if you have some arbitrary formula here, right? Wouldn't that make sense? You wouldn't typically get the same thing in the end. Like if you tried v equals t squared or something. The derivative is 2t, and negative 9.8 minus t squared does not equal 2t for all t. They're not the same function. So you're just trusting me here. What would this mean? What would the graph of this look like? And by the way, when we use the initial velocity of 20 meters per second, we can solve for c. E to the 0 is 1. So c, if I add 9.8 to both sides, is 29.8. If our initial velocity is 20. And we get v is negative 9.8 plus 29.8 e to the negative t. What does the graph of that look like? V is a function of t. Well, when t is 0, plug in t equals 0 here, you get either 0 is 1, 29.8 minus 9.8, you get 20. And as t gets bigger and bigger, e to the negative t is getting smaller and smaller. This part's going to 0. And so the whole function is approaching negative 9.8 plus 0, negative 9.8. That's a horizontal asymptote for this graph. It looks like an exponential decay toward that horizontal line. What is this telling you about the velocity? We threw the ball upward, initial velocity positive 20, it's going upward, but it does slow down in the positive direction. So it keeps going up until this time when it reaches the maximum height, I guess. And then it starts going down because the velocity becomes negative, but the velocity never goes above, so to speak, 9.8 meters per second in the downward direction. It never gets below negative 9.8 meters per second as a velocity. It's reaching something called a terminal velocity, in fact. That's the terminal velocity. It's an artifact of the fact that I chose M and K to be 1, that this happened to be 9.8. It is in meters per second, not meters per second squared. If I picked something different for M and K, I wouldn't have gotten 9.8. What about the height? There's the velocity. It's a function of t. I can just integrate that in the ordinary way to find the height. This is dh dt. I don't have to separate variables there because there's no h's over there. That's just a plain old function of t. Actually, let me go ahead and use this form of it. Integrate, and you're going to get h is the integral of negative 9.8 plus 29.8 e to the negative t dt. That'll be negative 9.8 t minus 29.8 e to the negative t plus c. If I use the same initial height of 1.5, I can solve for c, add 29.8 to both sides. C will be 31.3 meters. So h itself will be negative 9.8 t minus 29.8 e to the negative t plus 31.3. So now I can try, once I got these formulas now I can try to do the same kinds of things that I did on Tuesday. I can solve for when the height is 0, set this equal to 0 and solve for t. I can also solve for the maximum height by setting this equal to 0 and solving for t. The maximum height is still when the velocity is 0. And I can find the actual maximum height by plugging that value t back into this function. Let's do that quick with Mathematica. Oh, there we go. Okay, so I'll go ahead and use function notation here. H of t is going to be negative 9.8 t minus 29.8 t e to the negative t plus 31.3. Enter that function. Plot it. Let's just see what the plot looks like. Looks like that. We can see visually, looks like it's going to hit the ground slightly over 3 seconds. This is the height as a function of t. If you tried to solve this symbolically, set this equal to 0 and solve for t. If you tried to solve it by hand, maybe with calculator help, you would not be successful unless you graphed it in your calculator and used the root finding feature in the calculator. Because it's not a function that's solvable with ordinary inverse functions like logarithms. Yes, there's an e to the t in there, e to the negative t. But because this extra t here, you can't solve it. Now, Mathematica will solve it. If I say solve h of t equals 0 for t, it will give an answer of slightly bigger than 3, though with a little beep. It's saying danger, inverse functions being used. That's not always a problem. This is the correct answer to that many decimal places. However, you should realize that Mathematica is not really doing it in a way that you could do it by hand. It's using a function you've never heard of before called the product log function. It's not a function you learn about in any classes that you've had before this class. So it's kind of cheating in a way. So in general, you'd want to use find root. But remember to give a guess like 3. And there we go. Same answer. So rounding, say 3.05 seconds, that would be our answer. Oops. And technically speaking, you must do it, quote unquote, numerically on your calculator, graph it, use the root finding feature on your calculator. In Mathematica, the best thing to do in general is to use find root. That's predicting a little over 3 seconds. If, again, I had used a different M and a different K, I would have gotten a different answer. So I'm not really comparing this versus the quadratic model we did on Tuesday where we got over 4 seconds. It's not really a direct comparison because the mass there didn't matter for one thing. And I don't know what K to use. I'm just making up a K to be 1. So it's not really directly comparable to that. And again, is this right for a certain ball or a certain feather or whatever? You'd have to compare with experiment to see if it's right. More fundamentally, if you're wondering whether the model is right, by model, I mean this differential equation, or this one up here, more particularly this air resistance model, to know whether that's right, you'd want to do lots of experiments. Probably shoot the ball with a bunch of different velocities, measure how long it takes to hit the ground, compare with the prediction, and seeing how good the predictions are. The prediction, again, of being 3.05 seconds in this case. You could, by hand, figure out where this velocity is 0, set this equal to 0, solve for t, use logarithms. That would be doable for you. Maybe I'll have you do that in the assignment due next Tuesday. That could be done with logarithms. In calculators, you wouldn't need to graph it or use Mathematica. Logarithms would be good enough. And once you found that value t, you could then, again, plug it into the height function to figure out the actual maximum height. I think it's good, even though our class is not really about applications in the main, to spend some time talking about applications, mostly physics and finance, like I mentioned, to help motivate us for why we'd want to study this stuff.